Hello, everyone. In this lesson, we are going to learn how to graph polar coordinates and polar equations, and we're going to then investigate some special types of polar equations. But before we jump into polar equations, let's think for a moment about the graphs that we're more used to working with. In the Cartesian coordinate system, we know that we can get to any point in the plane by starting at the origin and moving a certain amount in the horizontal direction and then a certain amount in the vertical direction. So all points in the plane are determined by their x-coordinate and y-coordinate in this Cartesian coordinate system. The x-coordinate represents horizontal distance from the origin. The y-coordinate represents vertical distance from the origin. And because of that, when we graph points in the Cartesian plane, we use a rectangular grid. We only need to move left, right, up, or down to get to any point in the plane. But there's another way that we can get to points in the plane. Instead of thinking about how far left or right we're going to move from the origin and then how far up or down, we can think of an angle whose initial side is lying on the positive x-axis. And we are going to choose the angle so that the terminal side passes through the point in the plane where we are trying to go. Once we've determined that angle, then the only other thing we need to know to get to our point is its distance from the origin. How far away is it from the origin? So this distance right here. And this way of thinking about movement to points in the plane is called the polar coordinate system. It also requires two pieces of information, but they're different kinds of information. In the polar coordinate system, points are identified by their magnitude and direction from the origin. So the magnitude is that distance from the origin to the point, and the direction is determined by the angle, whose initial side is on the positive x-axis. Now, in the polar coordinate system, because we're using angles and magnitudes to get to points in the plane, our graph paper or our grid is going to look a little different. Instead of a rectangular grid, now we have this circular grid. Where the units of measure here, or when we're thinking about the scale that we're using, notice that it's just the radius of each one of these circles. So here, if we go a distance of 1, we are on a circle with radius 1. If we go a distance of 2, we're on a circle with radius 2, and so forth. And I don't have to just move along this positive x-axis. I could move anywhere in the plane. And so if I'm going to my point right here, I'm moving 1 radius, 2 radii, 3 radii, and then not quite 4, maybe about 3.5 radii to get to the point where I'm trying to go. And then, of course, we also need to know the angle whose terminal side passes through that point. So now, instead of having ordered pairs x, comma, y in the polar coordinate system, our values look like r, comma, theta. So r is the magnitude and theta that angle. And notice that the point we have plotted here in the plane is the same point under both of these coordinate systems. It's in the same place in reference to the origin. If we go back and look at it on the rectangular grid, it is in the exact same spot. It's 3 units to the right of the origin, 2 units up. And then here in the polar coordinate system, I could still go 3 units to the right, which would take me right here, and then 2 units up. So this is just another way to get to that point. So every point can be represented in Cartesian form with coordinates x, comma, y, or in polar form with coordinates r, comma, theta. And here we see these two coordinate grids superimposed one on top of the other. So again, the point that we were just looking at was in the rectangular system, the point with coordinates 3, comma, 2. So this point right here. But we can also get to that point in the polar coordinate system by finding this angle and then measuring this distance, r. And in the Cartesian coordinate system, the point with coordinates 0, 0 is called the origin. And that is this point right here. In the polar coordinate system, that point is called the pole. And the positive x-axis here is called the polar axis. Now, unlike the Cartesian coordinate system, points in the polar coordinate system are not uniquely represented. You can have 2 points in the polar coordinate system that have different coordinates, but actually represent the same point. For example, let's look at the point with polar coordinates 4, pi over 6. Now to plot this point, you can either start with the r value or start with the theta value. Let me show you both ways. If I start with the r value, then what I'm saying is from the pole, I'm going to extend outward a radius of 4. So this graph doesn't have a scale labeled, but we'll assume each one of the radii shown here is 1 unit. So if that's 1, 2, 3, 4, I'm going to extend from the pole outward 4, which is going to take me right here. Now that's not the point I'm trying to plot, just showing you that this is where visually I'm looking first. I'm going to go outward a distance of 4, and from there I'm going to rotate around in a counterclockwise direction an angle of pi over 6. And pi over 6 is 30 degrees, so that is going to land right here, because this angle right here is pi over 6, or 30 degrees. So here's my point with polar coordinates 4, pi over 6. Now let's try that again. Here I started with the r value and then adjusted for my theta, but let's do that in reverse. So let's start with the pi over 6. We still have a point with coordinates 4, pi over 6, but I'm going to start thinking about the pi over 6 first. So I would identify the angle pi over 6, and that's this angle right here, pi over 6. And then from the pole, I'm going to follow along that terminal side of that angle 4 units. So 1, 2, 3, 4. And that takes me to that point right there. And the same is true in the Cartesian coordinate system. You, starting at the origin, you can go right or left first and then up or down, or you could go up or down first and then right or left. You're still going to land in the same spot. Now, can we think of another set of coordinates that are going to take us to this same point? There's a couple ways that we can think about this. We can just think about, are there any other angles that terminate at that same spot? So I graphed the angle pi over 6 for this angle right here, pi over 6, from the polar axis or the positive x-axis to the terminal side, and that was pi over 6. But I could have also thought of my angle as being 2 pi, so traveling all the way around the circle, 2 pi, and then continuing on an extra pi over 6. That angle would also terminate in the same place here. So that angle would be 2 pi plus pi over 6, or pi over 6 plus 2 pi. And then I would still go outward 4 from the pole. So the polar coordinates 4, 2 pi plus pi over 6 actually represents the same point as the point with polar coordinates 4, pi over 6. And hopefully you can imagine there are lots of ways we can do this. There are lots of angles that terminate in that same place. In fact, there's infinitely many angles that terminate in that same place. All we have to do is keep adding 2 pi to our angle, or even subtracting 2 pi. I could go from my polar axis, I could go in a clockwise direction and rotate around and stop when I get right here. And that would also terminate in the same place. So lots of possibilities. We can actually say 4, pi over 6 plus any multiple of 2 pi or minus any multiple of 2 pi. So plus 2 pi k, where k is just some integer. So that represents lots of possible ways we can write polar coordinates for the same point. But there's another way. We can do this also by adjusting the value of r. Now we still need to move out 4 units. But in all of the angles I've shown you, or in all of the points that I've shown you here, I was moving in a positive r direction, meaning from the vertex of my angle, I was traveling along the terminal side of the angle. But let's consider the angle that starts on the polar axis and terminates right here. So this is not the angle pi over 6. It's the angle pi over 6 plus pi, or 7 pi over 6. Now, if I use the angle 7 pi over 6 and an r value of positive 4, my point would be right here. This is 4 comma 7 pi over 6. Because we move from the pole along the terminal side of the angle. That's considered a positive r direction. But if I move in the opposite direction from that, that would be a negative r value. So I could go to an angle of 7 pi over 6, and instead of moving forwards 4 units, I could move backwards 4 units, which would take me right here. So negative 4 comma 7 pi over 6 is another way we can write the coordinates of this point. So lots of ways to represent polar coordinates. And the pole is located, of course, at an r value of 0. But what about the angle? Well, if we say the angle is 0, then the angle just looks like the positive x-axis or the polar axis. So that works. We go to an angle of 0, and then the r value, the distance we travel from the pole, is just 0. So we're just stuck right there at the pole. So definitely that works, 0, 0. But that's not the only way we can represent the pole. Any angle will work if r is 0. We could rotate to pi over 2, for example, and this would be our angle here, pi over 2. But if the r value is 0, I'm still stuck right there at the pole. So in general, we can say that the pole is represented by the coordinates 0, comma, theta. It will work for any value of theta. In the following exercise, you're asked to graph and label each of the following points, A, B, C, D, E. So pause here and see if you can plot these points. And when you're ready to check your answer, you can hit play again. For point A, we're going to use an angle of pi over 4 and an r value or a radius of 3. So I find it a little easier to think about the r first. I'm going to go out a radius of 3, which is taking me right here. And then I'm going to rotate counterclockwise pi over 4, which would be this point right here. So there is my point A. Now point B has a radius of 2 and an angle of negative pi over 4. So radius of 2 takes me here, and then negative pi over 4, we're just going clockwise, which would be this point right here for point B. Point C, the r value is 0, so no matter what my theta value is, I know that point is at the pole, point C. Point D, now negative 1, instead of going in the positive r direction, I'm actually going to go in the negative r direction. For negative r values, it might be easier to start with the angle. I think it would be easier to start with the angle. So I'm thinking pi over 2, and I know pi over 2 is this angle right here. And I need to go negative 1, so the opposite direction will put me right here, point D. Point E, now this one also has a negative r value, so I'm going to go to the angle first and then move away from the terminal side instead of along the terminal side. So negative pi over 4, that's the same angle we saw for point B, but we're going to go negative 3. So I have to back up 1, 2, 3 right here. That would be point E. And finally here, we're going to re-express the coordinates of the point 2 comma 3 pi over 4. There's lots of ways to do this. You don't have to do it the way that I'm going to do it. The easiest way to re-express the coordinates would be to add 2 pi to the angle. So we have 3 pi over 4 plus 2 pi, and my 2 pi, I want to get a common denominator here. So I'm thinking of that as 8 pi over 4. So my coordinates are 2, comma, 11 pi over 4. You can add any multiple of 2 pi, you can subtract any multiple of 2 pi, or you can even change the 2 to a negative 2 and then add pi to the angle, or multiples, odd multiples of pi, or subtract odd multiples of pi. So we've seen that we can represent the same point using Cartesian coordinates or polar coordinates. Now we're going to talk about how we switch back and forth between these two coordinate systems. For any point in the plane, other than a point on the x or y axis, but any point other than that, we can make a right triangle with the x-axis. And when we do that, we can use our right triangle trig ratios here. The cosine of theta would be the length of the adjacent leg over the length of the hypotenuse, that ratio, adjacent over hypotenuse. Well, how long is the adjacent leg and how long is the opposite leg here? We don't want to use 3 and 2 necessarily, because then we're only defining that for this one specific example. We want to try and keep this general. So in general, this point that is labeled r comma theta also has Cartesian coordinates x comma y. And we know to get to this point from the origin, that means we're traveling right a distance of x and up a distance of y, which tells me that this leg in this triangle has a length of x. And this leg of this triangle has a length of y. So now the cosine of the angle theta is x over r. And the sine of theta is the length of that opposite side over the length of the hypotenuse. So that would be y over r. If cosine theta equals x over r, and we multiply both sides of that equation by r, then we get the result x equals r cosine theta. Similarly, from sine theta equals y over r, if we multiply both sides by r, then we have y equals r times the sine of theta. And x squared plus y squared, if I square the equations in numbers 1 and 2, and then add the left-hand sides, add the right-hand sides, I get, let's do that individually. So here x squared equals r squared cosine squared theta, and y squared equals r squared sine squared theta. Now adding the left-hand sides gives me x squared plus y squared, and adding the right-hand sides gives me r squared cosine squared theta plus r squared sine squared theta, and we can factor out the r squared, leaving cosine squared theta plus sine squared theta, which we know from the Pythagorean identity is equal to 1. So now this simplifies to just x squared plus y squared equals r squared. And then y over x, well, we already have an equation for y and an equation for x. So y over x would be r sine theta over r cosine theta. We can cancel out the r's here, and we're just left with y over x equals sine theta over cosine theta, which we can also write as tan theta. So y over x equals tan theta. Now these first two equations are going to help us convert from polar coordinates to rectangular coordinates or Cartesian coordinates. And the second pair of equations then are going to help us convert our rectangular coordinates into polar coordinates. So again, these two equations are going to help us go from polar to rectangular. And then these two equations from rectangular to polar. In this next example, we are converting polar coordinates to rectangular coordinates. So one thing we can do here is just to plot this point. We have the polar coordinates. We know that r is 2 and our angle is pi. So that would be this point right here. And because that point is right on the x-axis there, it's very easy to see what the rectangular coordinates should be. We should be getting -2, 0 for our answer. But that's going to be more of a way to check. Let's see if we can do this using our conversion equations. So in number 1, we know that r equals 2, and we know that theta equals pi. To get our x coordinate, we just find r cosine theta. So 2 cosine pi. The cosine of pi is -1. So here we have x equals -2. And we know that y equals r times the sine of theta. So 2 times the sine of pi. The sine of pi is 0, and 2 times 0 is 0. So we have the Cartesian coordinates, x comma y, equals -2, 0. For number 2, we have the point with polar coordinates √3, pi over 6. So that one may be a little harder to plot just by looking if we don't know exactly how far √3 is from the pole. So let's just try and convert. Here we have x equals, we want r times the cosine of theta. So the r is √3 and the theta is pi over 6. √3 times the cosine of pi over 6. The cosine of pi over 6 is √3 over 2. So √3 times √3 over 2 is 3 over 2. And then y equals r, which is √3, times the sine of theta, so sine of pi over 6, pi over 6. And the sine of pi over 6 is 1/2. So √3 times 1/2 is √3 over 2. So we have rectangular coordinates or Cartesian coordinates, 3 over 2, comma, √3 over 2. And to plot this point, I'm actually going to use both the rectangular and the polar coordinates to help me out here. So it's easy to go into an x coordinate of 3 over 2, 1.5. I can see that's going to be like right there. Now, square root of 3 over 2, I don't know exactly how high up to go. However, from looking at the polar coordinates, I know I'm going to be landing on the terminal side of pi over 6. Pi over 6 is 30 degrees, so this might not be completely accurate, but I can approximate where 30 degrees is just by cutting that quadrant 1 into thirds. It would be about right there. And so 1.5, and we would go up, and our point is right here. Now let's try converting from rectangular coordinates to polar coordinates. These two examples are very easy to plot in the rectangular coordinate system. The point -1, 1, of course, is this point right here. And you can probably figure out the polar coordinates without too much trouble there. It's going to be an angle of not 45 degrees, but 45 degrees less than 180 degrees. And then the r value, we could make a little right triangle there. If we're going over 1 and up 1, then we can use Pythagorean theorem to find that hypotenuse length. But let's use our conversion equations. So we have the equation that tells us x squared plus y squared equals r squared. So x squared plus y squared equals r squared. And this tells me that r squared equals 2. So r equals the square root of 2. Now it could be positive root 2 or it could be negative root 2. You can use either r value, but you have to adjust your angle for whichever r value you're using, or you're going to end up in the wrong quadrant. Typically, it's easier to graph with positive r values, but you don't necessarily have to. We still need to find our angle theta. And there we know that y over x equals tan theta, or tan theta equals y over x. And here y over x would be 1 over negative 1, which is negative 1. And now we just have to figure out what angle has a tangent equal to negative 1. So we want the arctan, or tan inverse of negative 1, and that is negative pi over 4. Now, if I use root 2 comma negative pi over 4, I'm going to be in the wrong quadrant because negative pi over 4 is down here. And then if I use a positive r value, that's going to put me over here somewhere, which is not where I need to be. I need to be in quadrant 2. So I either have to adjust that angle or use a negative r value. If I want to use negative pi over 4 for my angle, then I can use negative root 2 for my r. If I want to use positive root 2 for my r, then I need to use this angle for my theta, which would be 3 pi over 4. Remember, there's many, many, many ways to write the coordinates for a point in the polar coordinate system. So I'm going to use 3 pi over 4 and then positive root 2. So r comma theta root 2, 3 pi over 4. Now for number 2, again, this one is very easy to plot in the rectangular coordinate system. 0, 2 would be, of course, this point right here. And that's also really easy to write polar coordinates for straight away. We can just use the angle pi over 2, and we can see that the r value is 2. But let's use our conversion equations to see how we can work this out for problems where it's not so obvious. So again, we'll use x squared plus y squared to get r squared. X squared plus y squared equals r squared. So I have r squared equals 4, and that means r equals plus or minus 2. I can choose 2 or negative 2. Just have to make sure that I choose the appropriate angle so that I'm landing in the right place. Now, you're not always going to be asked to graph your point when you're converting coordinates, but it's a good idea to always think about the graph because it's easy to mix up your angle with whether r should be positive or negative. All right, so I've got r equals 2. You might even want to just write r equals plus or minus 2, and then hopefully that will remind you that you do need to be really careful about your angle, possibly adjust your angle. So we have tan theta equals y over x, so 2 over 0. So we want tan inverse of, now wait a minute, what is 2 divided by 0? Well, 2 divided by 0 is undefined, but that is telling me something about my angle theta. Where is it that tangent is undefined? So you should know what your parent function y equals tan theta looks like when you graph it. We've got vertical asymptotes every pi units, and that one passes through the origin, and it looks like this. So this is pi over 2 here, this is negative pi over 2 here, and that is indicating to me that the theta value is pi over 2. And that does match what we're seeing on our graph. If I use pi over 2, then I do want a positive r value. So my r theta would be 2 pi over 2. Next, we're going to take a polar equation, not just coordinates of a point, but a polar equation and convert it to rectangular form. So when your equation is in rectangular form, it should not have an r in it. It should not have a theta in it. We're going to convert to an equation that just has x's and y's. And we can still use those same 4 conversion formulas to help us out here. So I'm thinking about the formula that says x squared plus y squared equals r squared. If I square both sides of this equation here, I have r squared equals 4, and then I can make this substitution because r squared is x squared plus y squared. So now I have x squared plus y squared equals 4. And hopefully you recognize that as the equation of a circle centered at the origin with radius 2. So if we go back to our original polar equation, that is what this is saying. It's just saying that r equals 2. There is no theta in this equation. So the graph of this equation would be all the points that have an r value of 2. So for all of the possible theta values, r is 2. So when we sketch that, we're just going to get a circle with radius 2 centered at the origin. So here's another rather strange polar equation because this one doesn't have an r in it. Most polar equations are going to have both an r and a theta. This one just has theta, no r. And we see situations like this when we're working in rectangular form. Like sometimes we have an equation that only has a y in it, like y equals 3, or only has an x in it, x equals 2. So this is just one of those unusual types of equations. When we only have a theta, we don't have an r. So what conversion formulas do we have that are going to involve theta? Well, we have tan theta equals y over x. So we could take the tangent of both sides of our equation here, and that would give us tan theta on the left and tan pi over 3 on the right. Tan pi over 3 is a constant. We can evaluate that. That is one of our special angles from the unit circle. So tan theta equals, and this is the sine of pi over 3 over the cosine of pi over 3. So root 3 over 2 divided by 1/2 is just root 3. And tan theta is y over x. So y over x equals root 3. Now we've eliminated the theta from the equation. Our new equation here just has x's and y's in it. So this is our rectangular equation. And we can simplify it a bit more. By multiplying both sides by x, we have y equals the square root of 3 times x, which is a linear equation passing through the origin with a slope of root 3. Now, how do we graph that? Well, if you don't know exactly how far away root 3 is from the origin to do like a rise over run here, we can go back to the polar form of the equation. It's very simple to graph this polar equation. This polar equation says no matter what the r value is, the angle is always pi over 3. And pi over 3 is 60 degrees. So we can just eyeball that there. 60 degrees is about right there. So for all the possible r values, the angle is always pi over 3, which is just going to be this line passing through the origin with that slope. Next, we're trying to convert r equals secant theta into rectangular form. So here's a polar equation that has an r and a theta in it. So we might have to use more than one of our conversion formulas. Now, when I see secant theta, immediately I'm thinking 1 over cosine theta. Secant is the reciprocal of cosine. So we can rewrite this as r equals 1 over cosine theta. And thinking back to those 4 conversion equations that we have to work with, we have an equation for r cosine theta. So let's multiply both sides of this equation by cosine theta. R cosine theta equals 1. And r cosine theta is the same as x. So we have x equals 1. For our rectangular equation or Cartesian equation, r equals secant theta is the equivalent polar equation. X equals 1, we know, is a vertical line passing through all the points where the x coordinate is 1. Next, we're going to talk about symmetry. If opposite theta values produce the same R values, then we have a situation like we see in this picture here. So we have this angle theta. So we rotate theta and then we move forward from the pole a distance of R. But negative theta would just be the same size angle, but in the clockwise direction. So we would move along. That would be negative theta here. And if we're still moving forward R, we can see that the points are just going to be reflections of one another across that positive x-axis or that polar axis. So if opposite theta values produce the same R values in your polar equation, then your function is symmetric about the polar axis. Well, how would we check that? All we have to do is replace the theta or thetas in our equation with negative theta and make sure you put parentheses around the negative theta. If you do that and simplify the equation and you get the same equation you started with, then that polar equation has this type of symmetry, symmetry about the polar axis. Now, if you do check and that's not what happens, you don't get back to the original equation, it doesn't necessarily mean that it doesn't have this symmetry. In that case, it's just inconclusive. You might want to plot points to check. Let's look at an example. So here we're asked to sketch the graph of r equals 1 plus 2 cosine theta and test for symmetry about the polar axis. Now we could plot some points first and get a sense of what the graph looks like, or we could test for the symmetry first. If we test for the symmetry first, it's probably going to help us complete the graph, assuming that it does have the symmetry. If the test is inconclusive, then it really doesn't help us at all. Well, let's see what happens. So to test for symmetry about the polar axis, we're just replacing the theta with the negative theta. So our original polar equation, r equals 1 plus 2 cosine theta, becomes r equals 1 plus 2 cosine of negative theta. Again, remember to use parentheses there. And then we'll simplify using trig identities if we can. Now, there is an even-odd trig identity here. Cosine is an even function. And so we know that the cosine of negative theta does indeed equal the cosine of theta. So we have r equals 1 plus 2 cosine theta, which is the original function we started with. So I probably shouldn't call all of these things r. Let's say r1. r1 would be the new polar equation when we replace theta with negative theta. But we see that r1 is just equal to the original equation r. So we can conclude that our graph does have this type of symmetry. It is symmetric about the polar axis. And so really, if we just plot some points between 0 and pi, we can reflect those points to complete our graph. So let's do a quick table of values. And we'll say r theta, so 0, 0, or not 0, 0, making assumptions. Let's just start with r equals 0 and see what happens. Well, I could start with r equals 0 and solve for theta, but it's actually, hopefully you see, it would be a lot easier to substitute something in for theta and then determine the r value. So let's do that instead. Let's try theta equals 0, an angle of 0. So I'll come back up here, then r equals 1 plus 2 times the cosine of 0. The cosine of 0 is 1, so r equals 3. So I have, now these are polar coordinates, remember, these are not Cartesian coordinates. So 3, 0 means that our angle is 0 and our radius is 3. And we'll assume that we're counting by ones here. So we have that point right there. All right, what should we try next? We can try pi over 2. That's a pretty big jump. I'm looking at the equation and I'm thinking what's going to be easy to take the cosine of. It's easy to take the cosine of 60 degrees. So let's try that one next. And 60 degrees would be pi over 3 for the angle, pi over 3. And then r would be 1 plus 2 times the cosine of pi over 3. The cosine of pi over 3 is 1/2, times 2 is 1, plus 1 is 2. And on my grid here, pi over 6, pi over 3, pi over 4 right here in the middle. So our angle, pi over 3, gives us a radius of 2. We've got this point right here. All right, now let's try pi over 2. So r equals 1 plus 2 times the cosine of pi over 2. Well, the cosine of pi over 2 is 0, so that's just going to give me an r value of 1. So pi over 2, 1. Now from pi over 2 to pi is a pretty big jump. Let's just try that and see what happens. If we need to go back and use a different angle instead, we can. Or another angle instead, we can. So at pi, I've got 1 plus 2 cosine of pi. Cosine of pi is -1, so that would give me an r value of -1. Pi -1 is here. So that looks a bit strange now. I'm not sure what's happening between pi over 2 and pi. So I'm going to go back and try something else. Let's see. How about 2 pi over 3? I'm thinking of something that's going to be easy to substitute in. I'm trying to avoid getting the root 3 over 2. So 2 pi over 3, if we're subbing in 2 pi over 3, the cosine would be -1/2. So I would have 2 times -1/2 is -1 plus 1 is 0. And remember that one was in between. So if I'm thinking about my orientation of my curve, I'm going like here to here to here to here, and then somehow getting over here. But am I going straight across? No. So now let's try something. Still feel like we should get something in between maybe this point and this point here. When you have more experience working with these equations, you might just recognize what type of polar equation this is, and that will help you a lot when you're graphing. But it takes a little practice to get there. I'm going to go ahead and try 5 pi over 6 here. It's not going to be great, but it's kind of an in-between value that's going to help me get a little more detail on the graph here. So at 5 pi over 6, cosine is -√3 over 2. So we have 2 times -√3 over 2 plus 1, or 1 minus the square root of 3. Without a calculator, we know root 3 is somewhere between 1 and 2. A little closer to 2 than it is to 1. So if I had 1 minus 2, I'd be at -1. I'm not quite at -1, a little less. It's more like -0.7. So 5 over 6, we're going backwards. 5 pi over 6, going backwards. So along this angle here, not quite reaching the 1, about right here. Okay, so now I have a little better idea of what's going on with this graph. It's coming in like so, and here, and then by symmetry, I know we're going to finish this loop, come back around. Let me plot some of these points to make it easier. So by symmetry, I have a point here, and I'm following this one down to here. So the graph's going to continue around like that. Okay, so didn't really round it out enough right here. Should look more like that. And this kind of curve is called a limacon. And here's a nicer picture of that limacon. Now there are other types of symmetry. So what happens if we replace r and theta with -r, -theta? In the last example, we, instead of using theta r, we rotated around to negative theta and then used the same r. But here instead, here's our rotating around theta and going forward r. Now, if we go negative theta, so that would still be like what we were doing before with our negative theta. But now instead of going forward r, we're going to use a negative r. So we're going back r, like so, and landing here. And we can see on the graph that those 2 points are reflections across what we think of as the y-axis in the rectangular coordinate system. In the polar system, we would just say theta equals pi over 2. It's not really called an axis. So if opposite theta values produce opposite r values, then we have a polar equation that is going to be symmetric about theta equals pi over 2, or you can think of it as the y-axis. So how do we check that? Well, we're going to replace r with negative r, and we're going to replace theta with negative theta, and then we're going to simplify. And if the result is the same equation we started with, we know our function has this type of symmetry. For example, here we're asked to sketch r equals 3 sine theta and test for symmetry about theta equals pi over 2. Pi over 2. So our original equation is r equals 3 sine theta. And in my new equation, I'm going to replace r with negative r and theta with negative theta. Then we're going to simplify this and see what we get. Now, sine is an odd function. In the last example, we used the fact that cosine was an even function to simplify cosine of negative theta. Sine is an odd function, so we can use that odd property with our trig function here. Negative r equals 3 times, and we know the sine of negative theta is equal to negative sine theta. Okay, so sine negative theta gets replaced with negative sine theta, which means negative r equals negative 3 sine theta. Multiply both sides by negative 1, we have r equals 3 sine theta, and that is the same as the original equation that we started with. So the graph of r equals 3 sine theta is going to be symmetric about theta equals pi over 2, or about that y-axis. Okay, let's plot some points here. So we'll start with a theta value of 0. R equals 3 sine 0. The sine of 0 is 0, so we have r equals 0. 0, 0 is right there at the pole. And then let's try, again, I'm looking at my equation to choose something that's going to be easy to sub in for theta. Because I'm subbing it into a sine equation, I'm going to use pi over 6. The sine of pi over 6 is 1/2, so r equals 3 times 1/2, or about 1.5. So we'll go to pi over 6. Pi over 6 is right here, and a radius of 1.5 right there. Okay, pi over 2. That might be a big leap, but we'll see what happens. 3 times the sine of pi over 2 is 3. So pi over 2, 1, 2, 3, right there. Okay, so far my orientation is going like that, something like that. Let's try 5 pi over 6. Sine of 5 pi over 6 is 1/2 times 3, 1.5. And pi, sine of pi is 0. I'm back to 0 again. So those 4 points aren't a whole lot to go on. We might want to plot a few more. Let's do something between pi over 6 and pi over 2. We could do pi over 4. Let's just go ahead and go for pi over 3 here. Pi over 3. The sine of pi over 3 is root 3 over 2. So my r value is 3 root 3 over 2. We may need a little help from the calculator to figure out what that is. We can approximate it, but we don't want to be too far off here, or we're not going to get a good idea of what this graph looks like. Okay, so that's about 2.6. So 2.6. And then remember, we do know we have this symmetry to work with, so we're going to have another point right here. Okay, and orientation was coming around in this direction, and this does happen to be the graph of a circle. It is not centered at the pole, but it is a circle. R equals 3 sine theta. And here's a little better picture of that graph. Okay, one more type of symmetry we're going to look at. With this type of symmetry, we have opposite R values corresponding to the same theta values. So for this first point in the first quadrant, here's our angle theta. We're going forward R to take us to this point. If we use that same theta, okay, so I'm swinging around to this angle right here, but I go back R instead of forwards R, then I get to this opposite point over here. So they have the same theta value, but they have opposite R values. And in the rectangular coordinate system, that's the situation where you have opposite X values produce opposite Y values. So this is symmetry about the origin. How do we check for symmetry about the origin or about the pole here? We're going to replace the R with a negative R only, and then simplify the equation and see if we get the original equation back. For example, let's consider this polar equation, r squared equals 4 cosine 2 theta. We're going to test for symmetry about the origin, so we're going to replace the r with a negative r, and then simplify. Well, negative r squared is r squared, so right away we get back to the original equation. So yes, this graph will have symmetry about the origin. Okay, let's plot some points. We'll start with a theta value of 0. R squared equals 4 times the cosine of 2 times 0. And the cosine of 0 is 1, so we have r squared equals 4. So that would mean that r equals plus or minus 2. So an angle of 0, here's r equals positive 2, here's r equals negative 2. Okay, what do we want to try next? So it's easy to take the cosine of pi over 3, but we're actually taking the cosine of twice our angle. So I want to divide pi over 3 by 2, which gives me pi over 6, to get something that's easy to substitute in for theta. So we'll substitute pi over 6. When we multiply it by 2, it becomes pi over 3. The cosine of pi over 3 is 1/2. We multiply that by 4, we get 2. So r squared equals 2, then r equals plus or minus the square root of 2. Square root of 2 is approximately 1.4. So pi over 6, that's this angle right here. And we're going to go a little less than 1.5 radii in that direction, and then we can do the same thing in the opposite direction, a little less than 1.5. Okay, and so orientation like so and like so. Okay, let's try pi over 2. 2 times pi over 2 is pi. The cosine of pi is negative 1. So that's going to say r squared equals negative 4. That's not going to work out for us. So we have a domain restriction here because we're not going to be able to take the square root of a negative value here. We only want positive cosine values, so we're not going to use pi over 2. Let's try pi over 3. Pi over 3, we multiply it by 2, we get 2 pi over 3. The cosine of 2 pi over 3 is negative 1/2. Negative 1/2 times 4. That one's still not going to work. Okay, maybe we'll have better luck with pi over 4. Pi over 4 times 2 is pi over 2. The cosine of pi over 2 is 0. Aha. So that's where we're crossing over then into negative values. 0 times 4 is 0, r squared equals 0. So we're back at the origin there. Okay, so we're coming around like this, and then we're going to have a break in our domain. And at the same time, I think we're coming around like this as well. So pi over 4 is where we first started having issues there. And that's going to probably last until like all of here, that range of angles right there is going to be a no-go because we're going to get negative cosine values. Let's see what happens when we use pi. So pi multiplied by 2, the cosine will be 1, and then we get r squared equals 4. So we're back to plus or minus 2. Okay, so now I guess the question is, because that's a repeat of what the work we've already done, is what's happening in here. So let us try 5 pi over 6. 5 pi over 6. 5 pi over 6. We're multiplying by 2, so we'll have 5 pi over 3. The cosine of 5 pi over 3 is 1/2. Times 4 is 2. So r squared equals 2. That is going to mean r equals plus or minus root 2. I have 5 pi over 6. So 5 pi over 6, we're going to go out root 2, which is about right there. And then negative root 2, which is about right there. So what we're getting here is like this figure 8 with an orientation like so. And this type of polar equation does have a special name. This family of curves are called lemniscates. And here's a better view of that graph. All right, let's take a break from graphing things by hand. Here, I would like you to graph this equation using your graphing calculator. So switch to polar mode in your calculator. You're going to hit the mode button and change from function mode to polar mode. When you're in polar mode and you hit your y equals button, instead of seeing y1 equals, you are going to see r1 equals, because our polar equations are going to be, for the most part, in the form of r equals and then some function of theta. And when you go into your window settings, now you're going to see options for your x min and max and your y min and max, because when we produce the graph, we're going to be seeing it on an x-axis and y-axis, but you're also going to have to enter in the domain for your theta values. So you'll have a theta min and a theta max and a theta step. Now the theta step, it's going to work just like we saw in parametric mode, that t-step. If you play around with the theta step, you're going to get vastly different results. So you want to keep that theta step nice and small so you get a nice smooth looking curve, but not too small or it's going to graph very slowly. Okay, so pause here so I don't spoil the graph for you. I want you to try graphing it on your calculator and see what you get. Make sure that your theta values are going from negative 8 pi to positive 8 pi. Okay, now you should be seeing something like this. Now I know that your graphing calculator doesn't have a square window, so you can square it up by adjusting your window settings. You can try zoom square and see if that works as well. And let's do one more graphing on the calculator. This time we're going to use theta values from negative 5 pi to positive 5 pi. So pause here, see if you can produce this graph on your graphing calculator, and then press play when you're ready to see the results. And there we have it. So we can get some really intricate designs when we're graphing polar equations. Now, obviously, this is not a function in the Cartesian coordinate system. And just like we saw with our parametric equations, we could find the arc length of this graph just from that one single equation, as long as we're working in polar form. Now, to finish up this lesson, I'm going to ask you to follow this link to go to this Desmos activity, and you're going to be investigating some special kinds of polar graphs. So you'll be looking at circles, at lemniscates, at rose curves, and limacons. It's an interactive demonstration, so you'll be able to play with the sliders, adjust different parts of the equation, and see how that affects the graph. And then come back and fill in your notes once you've figured out what the general form of these equations is going to look like. And finally, I want you to, based on the observations you made in that interactive demonstration, I want you to think about these questions. How are the graphs of r equals a cosine theta and r equals a sine theta similar, and how are they different? What effect does the value a have on the graph of the lemniscate r squared equals a squared cosine 2 theta? What effect does the value a have on the graph of the rose curve r equals a cosine n theta? What effect does the value of n have on the rose curve r equals a cosine n theta? And then for your limacons, when is it that the limason has an inner loop versus a cusp or a dimple? So you should be able to answer those questions after going through that Desmos activity. Okay, and then our critical thinking question for this lesson, without using a calculator, explain how you would graph a polar equation. How would you determine an appropriate range of values for theta? So we did some examples together. Think about the process that we went through. What was it? What kinds of questions were we asking? How were we doing that without relying on the calculator? Thank you for watching. And in our next lesson, we are going to be bringing some calculus into polar equations and their graphs.